program. I am the great and powerful Miss Fortune. Now, for my first trick, I will show you this picture.
Abracadabra! Do you see the circles? The circles look like they're moving, don't they?
So, wondering how I did it? Well, a true magician never reveals her secrets. But this isn't magic. This is physics.
Let's start off by exploring optical illusions, which occur when you see something that isn't there or an action that isn't happening. The brain categorizes images automatically based on what it knows and what its surroundings are. If an image confuses what the brain knows to be true, you get an optical illusion. Two basic types of illusions are ambiguous illusions and impossible illusions. An ambiguous illusion is when there are multiple possible images. Technically, both are there, but your brain can only see one at a time. For example, which side is the back of this box? Is this a vase or an outline of two faces? This is an impossible image. Because it is so far from what the brain knows to be real, you can't interpret the image.
In these illusions, the trick wasn't played by light, but by your brain's method of processing. There are some illusions caused by unusual behavior of light. A great example is a mirage.
When it is hot, the temperature of the ground rises, and it increases the temperature of the air above it. As light passes through air of different temperatures, light bends and we see a mirage. A mirage is actually another image that we see in the wrong place. For example, in this desert mirage, what we see is actually the sky, but because it is in the wrong place, our brain interprets it as water reflecting the sky. We are familiar with mirages in the desert, but this is actually the same phenomena. Here, we see the image of the car in two places and assume it is the reflection of the car in water. This doesn't only happen when the ground is hot. Mirages can also occur where the air near the ground is cooler, such as on the ocean. Here, however, rather than seeing the image below the object, we see it above the object.
The next illusion is called the horizontal and vertical illusion. This illusion explores how the brain perceives the sensory information between the upper and the lower visual fields.
Which line is longer? Most people would say the vertical one, but look! They are actually the same length. This may be related to the way light reaches the eye because it is round. There seems to be an asymmetry in the visual field that allude to how the brain is interpreting the image. An experiment was done to test the altitude asymmetry, confirming whether the illusion looks bigger or smaller in different field ranges. A negative score indicates the illusion appears larger in the above field, while the positive score indicates the illusion appears larger in the below field. Many test results indicated a negative illusion asymmetry score, signifying that the illusion looks bigger in the above field than in the below field. The brain helps to localize objects by combining information about the position of the stimulus with information of the location of the eye itself in their perspective orbit. All in all, researchers believe that the brain may prioritize the sensory vision during the downward gaze differently than it perceives other sensory information, leading to the horizontal-vertical illusion.
There are many magic tricks physics can do with mirrors, too. Oh no, what happened to my face?
One of the coolest tricks to do with mirrors is placing two plane mirrors in parallel position. When you stand between the mirror and look into one mirror, it looks like you're seeing yourself multiple times into infinity. How does that happen? To understand how this occurs, let's first look at one flat plane mirror. In any mirror, we have what we call the incident ray, which is the light ray coming toward the mirror, and we have the reflected ray, which is the light ray that is reflected off of the mirror. The normal to the surface at the point of incidence is always perpendicular to the mirror. We assume that the incident ray, reflected ray, and the normal to the surface at the point of incidence all lie in the same plane. if an incident ray comes in at a certain angle and strikes the mirror, that ray will reflect off at a certain angle. In a flat plane mirror, we see that the angle of incidence is equal to the angle of reflection. Now let's look at two parallel mirrors. We will label the mirrors M1 and M2. Let's place an object in between the parallel mirrors and label it O. The reflection of that object over M1 will be labeled I1 for image 1. Notice that the distance between the object and mirror 1 is the same distance as the distance between image 1 and mirror 1. This is a very important concept that helps create this effect. Now, if we look at the object reflected from mirror 2, we see that image 2 is placed at the same distance as the distance between the original object and mirror 2. To get that infinity illusion, the reflection of image 1 is now reflected over mirror 2 to create image 3. Notice the distance between image 1 and mirror 2 is the same distance between image 3 and mirror 2. This is repeated for the reflection of image 3 across mirror 1 to get image 4. You can probably guess by now that you can take the reflections of image 3 and 4 and repeat the process over and over into infinity.
A popular internet illusion is the afterimage. Afterimages occur when the image continues to appear after the original object disappears.
A negative afterimage illusion occurs when there is an overstimulation of your photoreceptors that adapt to the focused image and start to lose sensitivity. When you see a certain color on an afterimage, all the wavelengths of light will bounce off the object into your eyes and stimulate the retinal region that adapts to that certain color. Certain photoreceptors in your retina absorb the light. Do you see a red, white, and blue flag now?
And finally, we are back to our first illusion. It's called illusory motion.
Illusory motion is a phenomenon that physicists and psychologists have tried to understand for years. It has something to do with the peripheral drift illusion, which is when your brain makes assumptions to fill in the details of what you see in your peripheral vision. Illusory motion can be composed of color-repeated asymmetric patterns, also known as RAP, which are used to enhance illusory motion strength. Past researchers and artists discovered that using sawtooth luminance patterns, as well as the combinations of black, dark gray, white, and light gray, can enhance the peripheral drift illusion. However, in 2006, a researcher named Kitaoka suggested that the certain color combinations such as blue-yellow or red-green can enhance the illusion even further. This concludes our look at optical illusions. I hope you learned a little more about how physics relates to your eyes and the world around you. There are thousands of illusions we couldn't learn about today, so go and explore!
Join us next week for part 1 of our special series on the unifying theory of physics, as Dr. Kortemeyer of Michigan State University combines the Standard Model and the theory of general relativity in a way the world may not be ready for.